Okay, we'll begin our lesson on properties of the dot product, and some of these are very important for our study of vectors. So we start with some of the same properties that we looked at already when we talked about vector addition and scalar multiplication. And let's think about each of these properties and why they make sense. So we're going to start with three vectors. We're going to need vector A, B, and C, and a scalar K. The commutative property is A dotted with B equal to B dotted with A. We'll think back to the definition of the dot product. Using the geometric definition of the dot product, you can see that A dotted with B is defined right here. Well, B dotted with A would just mean you would end up switching, the magnitude of A and B, and order of multiplication doesn't matter. So yeah, definitely the commutative property is going to hold. Even if we think about the algebraic definition of the dot product, assuming that, A is A1, A2, A3, and B is B1, B2, B3, there's your algebraic definition. Again, B dotted with A would just involve swapping the components here. And so since they're just numbers, it doesn't matter what order you multiply real numbers in. So because multiplication is commutative, so is the dot product. Okay, combining the dot product with scalar multiplication. So if you think of K as a number here, this kind of helps. So basically saying, look, you want to multiply A dotted with B times 3. This is not scalar multiplication here because A dotted with B is a scalar times a scalar. Basically, this property is saying that's going to be the same as 3A dotted with B. Well, that should make sense too. When you do A dotted with B, you do the magnitude of A times the magnitude of B times the cosine of the angle between them. If you want to triple that, one way of tripling it would be just to be triple the magnitude of A. That's going to do the exact same thing. Or you could, of course, triple the magnitude of B. Okay, which is exactly what's going on when it's written this way. Okay, so that one should make sense too. Next is the distributive property. This one's a little bit more interesting. If you add vectors B and C and dot it with A, the dot product is distributed over multiplication. Very similar to, the dot product is distributed over vector addition. Very similar to how regular multiplication of numbers is distributed over addition. This one might be a little bit surprising. We will actually look at this one and prove it and show why it works. And this is a very important, probably the most important property of the dot product is the fact that it is distributed, which makes the dot product of vectors behave somewhat similar to multiplication of regular numbers. And the last property we've looked at so far is the associative property, okay? The idea that if you want to dot three vectors together, it doesn't matter whether you dot the first two or the last two first. Now, this was true for vector addition. Is it true for the dot product? Think about that for a second. The answer is no, and the reason no is this is meaningless. This is garbage, okay? This is not true. Why is it not true? Well, A dotted with B dotted with C is meaningless. The reason it's meaningless is A dotted with B is a scalar. You can't dot a scalar with a vector. The dot product exists between two vectors only. This is not scalar multiplication because of the dot there. And so this just doesn't have any meaning, okay? It'd be like if you tried to say something like, here's another meaningless statement, 3 plus vector A. You cannot add a vector to a scalar. This has no meaning whatsoever, just like this has no meaning either. And finally, the last property you might include is that when you take a vector and dot it with itself, you get the magnitude of the vector squared. We looked at that in essays from yesterday, but from our last lesson, so that's nothing new. Okay, the distributive property is important. It allows us to now expand expressions with the dot product. And that means not only can we distribute the dot product over addition, we can actually use FOIL as well. FOIL is really just the distributive property used a few different times. So if I look at these examples, because I'm now dotting, I can expand this. I can say that this is the same as 2A dotted with 3A, okay, minus 2A dotted with B, plus 3A dotted with B,
minus b dotted with b, which is actually the magnitude of b squared. So I'm using the distributive property here. I mean, FOIL is the distributive property. Here's my first term, okay, if you're wondering where I'm getting this from. First, okay, outside, so 2a and negative b. So I inside, okay, b dotted with 3a gives me that right there. And then last, of course, negative b and b dotted gives you that right there. Now I'm using more than one of these properties. I mean, I'm definitely using this property right here, okay, to get this. I'm also using the idea that 2a dotted with, that, you know, the order doesn't matter either. So I did 3a dotted with b and I put the 3a first, okay. That sort of thing. Now the next thing I'm actually going to do, and I probably normally would do it right away, is 2a dotted with 3a is 6 times a dotted with a. So that's actually using this property up here, okay, by multiplying those together. So 6 times the magnitude of a squared. And then look at this. If you have 3, a dotted with b is going to be the same value. So these are like terms. 3ab minus 2ab is just a dotted with b. Kind of like expanding polynomials. Most of the time, you'd probably just go straight to this step right here. 2a dotted with 3a is 6 times a squared, the magnitude of a squared. And then the 2ab plus 3ab gives you the positive ab, a dotted with b, and then minus the magnitude of b squared. So it behaves a lot like a regular polynomial does, even though that's not what it is. Now for this, there's nothing else we can do with that. We don't know the magnitude of a, we don't know the magnitude of b. The only thing we could do is we could replace a dotted with b with the magnitude of a times the magnitude of b times the cosine of the angle between them, but I don't know the angle between them, so I don't think that that's going to be very helpful either, so I'd probably just leave it like that. Taking a look at the next one, same idea. 2i dotted with 3i is 6 times the magnitude of I squared. And then we're going to get a plus 4i dotted with j minus 3i dotted with j gives us just I dotted with j. And then the last term minus 2 times the magnitude of j squared. Now I notice a few things here. Notice that there are unit vector symbols here, meaning the magnitude of I and the magnitude of j is 1. So that means that this first term just becomes 6. And this last term here becomes negative 2. But also, I think it's a fair assumption here to assume that I and j are in fact the unit vectors. Remember those standard basis vectors we talked about? So this being I and this being j. Okay, I being the vector 1, 0, which has the, or 1, 0, 0 if we're in 3 dimensions. Okay, it goes along the positive x-axis. J is along the positive y-axis, so it's 0, 1 or 0, 1, 0 if you're in 3 dimensions. The point I'm trying to make here is even if you're in 2 or 3 dimensions, I and j are perpendicular vectors, which means that their dot product is going to be equal, sorry, I don't know why I deleted that, meaning that their dot product is going to be equal to 0. So the answer here is 6 minus 2, which is equal to 4. If I look at this next example, I'd like to point out that you don't need to know anything from this lesson to answer this problem. I could answer this problem by figuring out what 2a plus 3b is, because I know the magnitude of a, and I know the magnitude of b, and I know the angle between them. I could also figure out what 4a plus 5b is. Okay, I know the magnitude of each of the vectors, I know the angle between them. I could draw a picture. And then technically I could dot those two results together, but think about how difficult that would be. You'd have to figure out what this is, then you'd have to figure out what this is, then you'd have to figure out the angle between those two sums, which you could technically do in order to use the dot product. It would be a lot of work. Okay. There's a really simple way, though, if I use the distributive property, I find that this is not so difficult. 2a dotted with 4a is 8 times the magnitude of a squared. Next I get 10ab plus 12ab is 22ab. Of course, when I say ab, I mean a dotted with b, like so. And then finally, plus 15 times the magnitude of b squared. All right. Now, I know the magnitude of A is 3, so this is 8 times 3 squared. Just leave this part alone for now. I also know the magnitude of B is 2, so this is 2 squared. Now, 8 times 3 squared plus 15 times 2 squared gives you 132. So I have 132 plus, now how am I going to figure out what 22A dotted with B is? Well, this is equal to 22 times the magnitude of A times the magnitude of B times the cosine of the angle between them, which is 120 degrees. So that can actually, I can figure that out as well. I get 132 plus 22 times 3 times 2 times the cosine of 120. And because it's a special angle, the cosine of 120 is negative 1/2. So I end up getting 132. It's going to be take away 66 for my final answer of 66. And there you go. You're going to find in this portion of the vectors course, we start to get into some more challenging questions. And here's an example of one of those more challenging questions. So we have two vectors, 8u subtract v and 4u plus 3v, and those two vectors are perpendicular. That does not mean that u and v are perpendicular, okay? It's when you create these two sums that you end up getting two vectors that are perpendicular. So you need to understand the idea that that this vector this is a vector and this is a vector quantity. So and those two vectors are perpendicular. Now, what should I do as soon as I see the idea that two vectors are perpendicular? We should say that their dot product is equal to 0. So I'd write that down right away even. I know that 8u subtract v dotted with 4u plus 3v must be equal to 0. The dot product of perpendicular vectors is 0. In fact, if we go aside a little bit, we're dealing with 2- and 3-dimensional vectors in this course. Well, when you get into linear algebra, you deal with vectors of any dimension. And as it turns out, vectors of 4, 5, 6, 7 dimensions behave very similar to vectors in 3 dimensions. You just can't visualize what they look like, or certainly I can't. And when we talk about vectors in other dimensions, we can't really talk about them being perpendicular because we can't really visualize them intersecting at a right angle. But we can talk about their dot product being 0. And that's kind of our definition of perpendicularity in any dimension. That's not a word. The word's actually orthogonal. Orthogonal means perpendicular for vectors. So we might say these vectors are orthogonal, and the definition of orthogonal being their dot product is equal to 0. That's just a little bit aside. I'll probably mention that a few times as we go on. What does this stuff look like when you get into higher dimension other than 3? The answer is looks pretty much the same. You just can't visualize it on an XYZ axis anymore. Okay, continuing on with this example. Notice I haven't even used this idea that V is twice the magnitude of U. Although I have V and U in here, I don't have their magnitudes anywhere. Not surprising probably to not worry about that yet and realize that we can actually expand this, and let's try that. So we're going to get 32 times the magnitude of U squared. Okay, next I'm going to have a 24 UV minus a 4 UV is going to give me plus 20 times U dotted with V. And then finally at the end, subtract 3 times the magnitude of V squared equals 0. Now, I'm going to introduce a few things. First of all, I'm looking to find the angle between U and V. Second, I know that the magnitude of V is twice the magnitude of U, which means that I can say that the magnitude of V is equal to 2 times the magnitude of U. I'm going to do some replacing. I am going to replace the magnitude of V for sure using this formula right here. And I'm also going to introduce the magnitude of U and V and the angle by evaluating or expanding what this looks like. So I get 32 times the magnitude of U squared plus 20 times the magnitude of u times the magnitude of v times the cosine of the angle. Subtract 3 times, okay, if I replace v with 2u, technically I'm squaring that, so I got to be careful to include that idea. And it is 2 times the magnitude of u, just like that. Okay, so it's important that we square the 2 as well. We square that, so let's just look at that. We're going to get, oh, and on the next line, let's use this formula again. Okay, the magnitude of v is 2 times u, so I can replace that magnitude with 2u as well. And then here I'm going to get 4u, but times 3 is minus 12 times the magnitude of u equals 0. All right, we're going to clean this up. Let's see, we have, I don't think there's much I can do with this to start. I've got minus 12u, and then if you look here, you've got plus 40 times the magnitude of u squared. So u times u. Remember, u, the magnitude of u is a scalar. Okay, it's not a vector when you include the magnitude. So these are really numbers. 1, 2, 3, 4 numbers multiplied together. 20 times 2 gives you 40. And then, of course, times cos theta. That's still part of that. Minus 12 times the magnitude of vector u equals 0. Okay, I've realized I've made a mistake here as well. I'm sorry if I confused you here. And the mistake that I've made here is this right here. Let's just get rid of, okay. Right here, I'm squaring 2 to get 4. Times 3 gives me 12, but I also square the magnitude of u. So there's a magnitude of u squared there. And then when I take the negative 12 and subtract from 32, I get 20. So really I have 20 times the, and then this is equal to 0. Sorry about that. Okay, how do we solve this now? Okay, we have two unknowns. We're trying to solve for the angle, and we also don't know the magnitude. Well, this is actually kind of like a quadratic equation in a way. And there's something that when something's set to 0 and you're not sure how to solve it, in general, I'd say factoring is a good strategy. There's a common factor of 20 times the magnitude of u squared. That's a common factor. When I take that out, I get 1 plus 2 cos theta equals 0. And this is something I can solve. When you have two things that are multiplied together to equal 0, one of them has to be equal to 0. So one possibility is this right here equals 0. Now, 20 can't be 0. This would only be true if the magnitude of u is equal to 0. Let's just think about that possibility. So the magnitude of u is equal to 0. If we back up, we would then say, well, the magnitude of v is also equal to 0. And what's the angle between the vectors? Well, the angle between the vectors, there is no angle between the two 0 vectors. So technically, if these are 0 vectors, then these are also 0 vectors, and we could argue that they are perpendicular. This is often what's called the trivial solution. It doesn't really count. Although the question didn't say these were non-zero vectors, it kind of seems like they probably are. So here's one answer. One answer is, you know, u and v are the 0 vectors, and so these two vectors are 0 vectors, and the magnitude of v is twice the magnitude of u because 2 times 0 is still 0, and the whole problem is satisfied. It's not really the solution we're looking for, though. The other possibility, of course, is 1 plus 2 cos theta is equal to 0. If that is equal to true, that is true, pardon me, that means that cos theta is negative 1/2. And what angle does that happen for? Well, if you imagine Cartesian plane, it'd have to be, okay, negative 1/2, you have to be over here where this is negative 1, and this is 2. That would make this angle 60.
And so we're dealing
with 120 degrees. Okay. Keep in mind, of course, when you're dealing with cosine, yes, there's another solution down here as well, but the angle between two vectors can't be greater than 180 degrees, so we know it has to be there. It's a nice thing about cosine. The last thing I'd like to talk about in this example has to do with work. And work is a quantity that we deal with in physics. If you've taken physics in high school, you've probably seen work. Now, in high school physics class, I'm guessing work is described as the force exerted on something times the distance that the object moves. So, for example, if I lift a 20 kilogram mass, a distance of 1 meter, then the work done is 1 meter times the force exerted on the object. And then, of course, if you actually look at work, it's only the force that's directed in the same distance the object is traveling. So it's a little bit this confusing concept of work. We're going to talk about work right now. I'm going to talk about it fairly briefly. In fact, I've just taken this right out of your textbook. So this is in your textbook as well, just so you know. So it just explains what work is, okay? In physics, the word work has a narrow meaning. Work is done whenever a force acting on an object causes a displacement of the object from one position to another. For instance, work is done in the force of gravity when an object falls because the force displaces the object from a higher to a lower position. Well, it might seem like hard work to hold a heavy object. If you do not move it, you are doing no work. So the only work done when you hold a heavy object is when you actually pick it up off the ground. Now, keep in mind that force and displacement, which is distance plus direction, those are both vector quantities. So as it turns out, work is actually just the dot product. The dot product between the force acting on an object and the displacement caused by the force. Okay? And then this is, of course, just the definition of the dot product. If you were ever told that, if you're pulling on an object like this and it displaces the object this way, okay, well then work is you probably didn't talk about those as being vectors in a physics class, but the work done is the distance times the force, but only the component of the force that operates in the direction of the displacement, which brings us right back to what the dot product is. That's exactly what the dot product is. This value times the magnitude of the force operating in that direction, which we get by taking the magnitude of the force and multiplying it by the cosine of theta. So it all works out. Work is a scalar quantity, of course, because it's the dot product, and the unit is a joule. Let's look at just an example very quickly. So suppose a 25 kilogram box is located 8 meters up a ramp inclined at an angle of 18 degrees. Determine the work done by the force of gravity as the box slides to the bottom of the ramp. Okay, well, here's the picture. This is 18 degrees right here. This must be 72. There are two vectors. Sorry if it's a little blurry. The first vector is the force of gravity, which is our force, and the second vector is the displacement, okay, which slides down the ramp. The force of gravity has a magnitude of 245 newtons, 25 kilograms times 9.8 meters per second squared, okay, the force due to gravity, or newtons per kilogram is usually what I write instead of that, but it's fine. Therefore, the work done by gravity is the force due to gravity times the displacement, the force due to gravity dotted with the displacement, which is 245, the magnitude of the force of gravity, times the magnitude of the displacement, which is the 8 meters, okay, times the cosine of the angle between them, 72 degrees, and there's the answer. So I don't think it'd be very good to talk about the dot product without mentioning the application that it has in physics, which is that it is, in fact, the definition of work. If you took physics and you learned about work, and the definition seemed a little off or a little odd or a little confusing, maybe a little ambiguous, it's because it really should be defined in terms of vectors and the dot product of two vectors. Okay, there's some challenging questions in here, in particular number 23. And the hint I've given you for 23, there's two ways you can do it. And you can look at the solutions. I'll post solutions to most of these questions. There's two ways you can do it. One of them can actually be done with exact values, and you don't need a calculator if you can figure that out. Okay, good luck with those.